We're going to discuss cylindrical coordinates. Let's compare them first to rectangular coordinates. That's what we typically use. The rectangular coordinates are our standard x, y, z that we use. You know, x goes out in this direction, y comes out in this direction, z goes up that way. And we pick a point, we can label it again x, y, z, depending on how far it is in those directions. But cylindrical coordinates are based off of polar coordinates. So let's remind ourselves how those work. Cylindrical coordinates are not x, y, z, they are r, theta, z, where r and theta are the same as we used in polar coordinates. So let's look at a two-dimensional representation. So here's a point x, y. Here is 0, 0. The distance from here to here in the x direction is x, and from here to here is y. And that's how we give it that representation. If we're going to go to polar coordinates, this distance from here to here is r, and this angle measured from the x-axis is theta. So the point xy is also the point r theta. So how do we go from rectangular coordinates to cylindrical coordinates? Well, if we have a point xyz, we leave z alone and we get what we get, r, theta, z. That's how we express that. So let's take a look visually at how this can. So here's a point P. We're expressing it in polar coordinates, but notice we have our standard x, y, z orientation. So we come out a little bit in the x direction and a little bit in the y direction. We get to this point Q. So Q is the point xy. But Q is also the point r theta. Notice r is the distance from the origin to that point Q in the xy plane, and theta is the angle between the x-axis and that length r. And this point P could be thought of as xyz for sure, but it can also be thought of as r theta z. So r theta z is the cylindrical representation of that point. So let's take a look at how we can do these conversions. So in essence, it comes back to how it works in polar coordinates. So we have x here, y here, r here, theta here, with our right angle here. So we can recognize from Pythagoras that x squared plus y squared equals r squared. Hitting that with a square root, we could say the square root of x squared plus y squared is r. So that's a relationship there that we can think about. What else do we have? How can we get theta? Well, we're starting with x and y, right? We have x, we have y. The tangent of theta is opposite over adjacent. The tangent of theta is y over x. Therefore, theta would simply be the arctangent of y over x. So if I know x and y, I can get r, square root of x squared plus y squared. I can get theta, the inverse tangent of y over x. What if I know r and theta? Can I get x and y? For sure, that's the case as well. What's our relationship there? If I know r and theta, how do I get x? How do I get y? Well, we use trigonometry. So cosine of theta is adjacent over hypotenuse. Cosine of theta is x over r, so r cosine theta equals x. Similarly, sine of theta is y over r. So r sine theta equals y. But I'm saying nothing about z because, again, remember, the cylindrical coordinates compared to rectangular are x, y, z. Cylindrical are r theta z. So z stays the same. There is no need for us to change that as we go along. And then one of our goals is going to be to convert equations from one coordinate scheme to another. So what I'm going to ask next is, how can we convert the following? X squared plus y squared minus z squared equals 0. We want to convert that to a cylindrical coordinate equation. And do we recognize what this graph will be? Notice if we look in the xy plane, we have a single point. If we look here, x squared equals z squared intersecting lines. Y squared equals z squared intersecting lines. This will be an elliptic cone looking something like this. So how do we convert that into cylindrical coordinates? What do we have to remember? Well, x squared plus y squared is r squared. So we get r squared minus z squared is 0, or r squared equals z squared. Good enough. Now, can you say r equals z? Maybe, but we may lose the lower half of our elliptic cone. So I think it's probably better not to quite do it that way. So let's take a look at another kind of problem. We want to convert. So this time, let's go with 3x squared plus 3y squared minus 2xy plus z equals 17. Remember, z stays the same, and our goal is going to be convert to cylindrical coordinates. So we're going to factor out the 3 here to go 3 times x squared plus y squared, because we remember x squared plus y squared is r squared. And then we've got to think about how these are going to work. Z isn't going to change. Z is just z equals 17. So again, we're looking at our triangle here. Here's x, here's y, here's r, here's theta. We see x squared plus y squared is r squared, which is good. So I know I get 3r squared minus, what is x, what is y? How do I make sense of that? Well, we see cosine of theta is x over r. So r cosine theta is x. So I get minus 2x is r cos theta. And how about y? What is y? Well, same kind of thing, right? Sine of theta is y over r. So r sine theta is y. So we get r sine theta plus z equals 17. So we've done it. We've successfully converted this into cylindrical coordinates, but it's not terribly satisfying in this format. So let's see if we make this a little bit cleaner. So looking at this, then, where does that put us? We are at 3r squared minus r squared times 2 sine theta cos theta plus z. Again, that's fine. There's not one exact way to do this, but I guess I could appeal to an identity that we know, namely 2 sine theta cos theta is the same thing as sine 2 theta. And I could write this equation as 3r squared minus r squared times sine of 2 theta plus z equals 17. And you could solve for r, you could solve for z, you could even, I guess, in theory, solve for theta. But all I wanted you to do is I wanted you to convert this into an equation using cylindrical coordinates, and we have done that successfully. But let's see if we can go the other direction. If I give it to you in cylindrical coordinates, can we convert it back to rectangular coordinates? So that question will be as follows. So we want to convert 3r squared plus 2 tan theta plus 5r plus 1 to rectangular coordinates. So if we're going to do this, we need to, again, keep in mind our geometry. So we start with our triangle again. Here's x, here's y, here's r, and there's theta. Then we know x squared plus y squared is r squared. So we'll replace this r squared with x squared plus y squared. Plus 2 tan theta. What is tangent of theta? Tangent of theta is what? Tangent of theta is opposite over adjacent is y over x. You can see that here. Plus 5r. What is r? Well, if x squared plus y squared is r squared, r is simply the square root of x squared plus y squared. Equals 1. And again, there's much you could do with this to make it look a little bit cleaner. But that is essentially what we're looking for. We've converted it to rectangular coordinates. Maybe I'll at least do a little bit of distributive property here. 3x squared plus 3y squared plus 2y over x plus 5 times the square root of x squared plus y squared equals 1.